Welcome back to electrochemistry. Today I'm going to talk about Faradaic versus non-Faradaic processes. Faradaic processes, we have electron transfer between the electrode and solution. For example, you might have an electrode with some electrons at the Fermi level here. Here's the metal electrode. And I might transfer an electron to a redox couple, driving it from an oxidized species to a reduced species via O plus an electron going to R. Okay? So this is a typical process we might want to study in an electrochemical cell. But I can also have non-Faradaic processes. A non-Faradaic process, you have no electron transfer across this interface, but structure of the interface changes, okay? Structure of the charges at interface changes. So a good example of this would be the charging and discharging of a double layer. So if I have, again, here's another example. Let's get rid of the Fermi level here, and let's say this is the metal and this is the solution. If I charge the metal up with some electrons, and this solution contains ions in it, what's going to happen? Well, obviously, electrostatics will drive the positive ions close to the electrode surface, and we call this the double layer. And charging that double layer, okay, charging the double layer is a non-Faradaic process. Notice there was never any electron transfer across this interface, but I've changed the charge distribution at that interface. We'll go through these in some detail. Now, Faradaic processes are often what we want to study, but non-Faradaic processes are also always present. So we need to understand them and sometimes correct for them, sometimes use them in our electrochemical analysis. So let's start with our description of a non-Faradaic process. So a non-Faradaic process always occurs in conjunction with Faradaic processes. The non-Faradaic process is actually what's going to be responsible for changing the energy, raising the energy of the electrons in the electrode, or lowering the energy of the electrons in the electrode relative to where they're transferring in the electrolyte. Okay, so let's consider what we're going to call an ideal polarizable electrode. Okay, an ideal polarizable electrode means that no current flows across the electrode-electrolyte interface or electrode-solution interface as potential is changed of the electrode. So if we apply a force, we're going to change the energy of the electrons in the electrode, but there's going to be no current flowing across that interface. It's ideally polarizable, so no net current flows at steady state. This is analogous to a capacitor, and we'll see why that is. The capacitor has a circuit element here, and the capacitance, if you remember from your physics course, is defined as how much charge, Q, in coulombs is held in the capacitor, is held on the plates in the simple parallel plate capacitor, or at the electrode-electrolyte interface, right? Here's an electrode-electrolyte interface where we have solution and metal. There's charge held here, much like I can put charge on the plates of a capacitor. Okay, so it's the capacitance is a value that characterizes the geometry of the interface and tells you how much charge you can put on that interface per change in potential across the capacitor. So this is Q, charge in coulombs. E is the potential across capacitor. And this is electrostatic potential, I should say. We'll learn about other types of potential in this course, and it's very important to distinguish between the two. So this is the change in electrostatic potential across the capacitor, and that's going to be in volts. And this is the charge in coulombs. So what's a coulomb, right? So one thing to remember is Faraday's constant, right? Faraday's constant says that there's 96485 coulombs per mole of electrons, right? So a coulomb is literally defined as 1 amp for 1 second. So it's the charge passed in 1 amp for 1 second. Okay, so it's kind of an arbitrary definition, but we can convert it to moles of electrons passed with Faraday's constant. So at an electrode surface, we have non-Faradaic processes occurring. Okay, and those non-Faradaic processes are associated, as I mentioned, with charging and uncharging the metal electrode. So let's consider a metal now. Let's assume it's at an electrostatic potential phi m. That's the metal. Okay, and at that electrostatic potential, it has some negative charge at the surface. These are electrons that are at the surface. Now, if you remember from Gauss's law, all charge in a metal, in a conductor, has to reside at the surface. Otherwise, there would be an electric field inside the conductor that would drive the charge to the surface. So we'll just remind that Gauss's law, all charge at surface of metal. Okay, just so you remember that, you might put that down in your notes. So what's going to happen in the electrolyte? What's going to happen in the electrolyte? Well, we know in the bulk of the electrolyte, we have lots of free ions, right? And the electrolyte is an ionic conductor, so those ions can move. And just like Gauss's law says that we can't have charge in the bulk of a metal, we also can't have free charge in equilibrium in the bulk of a ionic conductor. So what's going to happen at this interface is we will move some of those positive charges here into what's called the double layer. Okay, and the double layer is actually pretty complicated. I'm going to draw it a little different now, actually. I'm going to draw it with a little bit more realistic structure. If you think about these positive charges, I won't draw this on every one, but these positive and negative charges are going to be coordinated by solvent molecules, okay? And this could be water, right? They're going to be coordinated by solvent molecules because the solvent's going to have a fairly large dipole moment. Most solvents are polar, especially the ones used in electrochemistry. And so these molecules, these positive cations in this case, they can't actually get directly next to the surface, right? Because those strongly bound waters or other solvent molecules will prevent that. So there's this is what forms essentially the capacitive layer. Now, also, because of thermal energy, the cations that screen the electrostatic field coming off of the negative charge on the electrode, are not all right at the surface. They'll actually be smeared out a little bit. So there's, a few cations that are compensated this charge moving away from the surface. And this length is called the Debye length, lambda. This is the distance over which electric fields are screened. And screening, of course, is just canceling out by moving charges around, right? So that's what this is happening here. The field that's coming off of this, right, this negative charge would give off a field. That field will attract the positive charges to the interface until the field is canceled out. Okay? And we'll learn about this in more detail as we talk about electrochemical potentials, because what's really happening is the electrochemical potentials are equilibrating. And it's a little bit more complicated because we also have to think about the concentration terms in the electrolyte. But, to first order, you can think about the electric field being screened at that interface by the movement of these positive charges. Now, the double layer can get even more complicated because you could have ions that have been stripped of their water shell and specifically chemically absorbed to the surface. Or, for example, imagine I had a surface of TiO2 and the surface had some hydroxyl groups on it, right? And I can protonate those hydroxyl groups, or I can deprotonate them. So that would give me some surface charge. Okay, often we do sigma as the charge density, and sigma s would be the surface charge density. So there might be some surface charge in that double layer. And these are all complications that will affect the detailed physics of the interface and charge transfer across the interface and our description. But in the simplest way, we're just going to treat this as a simple double layer capacitor for now. And that's going to get us really far in understanding this system. Now, just a few more things. There's a few more things that are defined here. One is the potential right here, phi I, and that's the IHP, or the inner Helmholtz potential. And then there's the potential of the solvated, after the solvated ions, and that's the OHP, the outer Helmholtz potential. And they're sort of telling you what the electrostatic potential is at different positions moving away from the interface. And the difference between phi I and phi m is related to the surface absorbed charge, right? The difference between phi m, phi I and the inner and outer Helmholtz potentials is related to the charge in the double layer. And then there's a region of the double layer, which we call the diffuse double layer, that can extend out pretty far. And that's just basically saying that entropy won't let all the ions be right at the interface. They're going to diffuse out a little bit over this sort of screening length, this lambda screening length. Okay, so we need to define a few more things, and that's that sigma metal, the charge density on the metal, so let's give that some units. That's going to be coulombs per centimeter squared, is the charge density on the metal, right, in this picture over here. That has to be equal and opposite to the charge density in the solution. So that's all the excess charge in this solution, which also has the same units. And we can break that up, right, into the sigma I, which is that at the inner surface, plus sigma D, which is the rest of it going out into the diffuse double layer. So this is just important to remember, because on a capacitor, you have to have equal and opposite charge on the two plates. So this is just a statement of charge conservation. Now let's consider the double layer capacitance and charging. And charging that double layer capacitance. So let's consider a very simple cell. So consider this, a cell where we have, say, a 2-compartment cell with a glass frit in between, okay? One compartment is going to hold our working electrode, one's going to hold our counter electrode. So here's our counter electrode over here. We're going to have a, this could be, say, a saturated calomel, SCE. And let's say we have a disc here, or a flag of platinum. Okay, platinum. This is a platinum flag. And we could have a, this is going to be our counter electrode and our reference electrode, because this is actually going to be a 2-electrode system. Okay, we'll keep it simple. Because we're not going to pass much current, because we're just going to look at the non-Faradaic processes that are occurring. Okay, how would we represent this in a circuit model? So imagine we have a voltage source, E, right? And we can measure current, I. Measure current. Okay, so we have a voltage source, E, and we can measure current, I, and we take that to a mechanical switch, okay, that we can turn on and off. So we can turn on and off the application of the voltage. And we take that to our electrochemical cell, okay? So what's our electrochemical cell going to look like? Like, what are the elements in this electrochemical cell that we need to consider? Well, in order to pass current, right, we're going to assume that this reference electrode can pass current very easily. It's a ideally actually non-polarizable electrode, so it can pass current essentially without resistance. The voltage on this reference electrode is never going to change for the magnitude of the currents we're going to pass in this experiment. Okay, so we only have to think about electrode processes that are going to happen at the working electrode, the platinum disc. So the first thing we can do, if we're going to pass current, is we need to move that current through the electrolyte. So I'm going to define that as a solution resistance, RS, in this equivalent circuit. And then the other thing that has to happen if you want to charge, if you want to pass current in this cell, and you're not doing Faradaic chemistry, right? Faradaic chemistry, O plus an electron going to R. We are not going to do any of that, right? This is all non-Faradaic. The other thing we have to do, the only way we can pass current then, is charging up the capacitor that represents this interface over here, this electrolyte-electrode interface. So let's consider a simple experiment now. A simple experiment called a potential step experiment. So we'll consider the situation where when this switch is open, the potential is the same on both sides of this circuit of our electrochemical cell. And then when we close the switch, all of a sudden we're now applying a potential E from our source. It could be a battery, for example. Okay, so what's going to go on in this potential step experiment? So let's think about what we know. We know the Q, the charge on the capacitor, is equal to the capacitance times the potential across the capacitor, right? So this is just by definition of the capacitance. And this is CD. I'm calling that CD. That's the double layer capacitance of our system. So we know that. That's just by definition. And I also know that the total voltage, E, across this cell, right, from here to here, or the output across the two terminals of our voltage source, E, can be split up into a component across the resistor plus a component across the capacitor, right? So this is the voltage across the capacitor plus the voltage across the resistor has to equal the total voltage, okay? So that's pretty simple. Now, how can I write expressions for these? So what's the voltage across the resistor in terms of the current flowing through the cell? Well, we can use Ohm's law for that. So you should all have Ohm's law, V equals IR, burned in your head. Or in this case, let's use E equals IR, because Bard likes to use E for potential. So I can write now IRS, because that's going to be the voltage drop across there. And now, what about the capacitor? Well, the voltage across the capacitor is just Q over CD from this equation here, right? Now, the current, I need to right? The current here is, how do I understand how to write the current in terms of maybe some of these other things in this expression? So the current, by definition, right? What's its units? It's amps per. It's amps, which is defined as coulombs per second, right? So I think about current. It's really dq dt. It's the amount of charge that flows, the changes in charge per second, is going to be equal to the current. Okay, and that's going to be a charge Q on the capacitor, because the charge on the capacitor, right, that's where the current is going. So I is going to be dq dt. So I can plug that in there. dq dt rs plus q over cd. Okay, so now I have an expression here, because what I want to do, right, as I want to solve this, I want to understand, as a function of how I apply this potential, I want to understand what the charge on the capacitor is. And if I know the charge on the capacitor, I can, as a function of time, I can also calculate the current as a function of time. RS and CD are all things that we know they're parameters of the system. So let's see if we can solve this equation. So think about this. How would you solve this equation, right? How would you solve this equation in terms of dq dt? Well, we need to figure that out, right? So I can write this. dq dt is just equal to negative q over rscd plus e over rs. Okay, so this is just this expression rearranged. And this is, of course, a differential expression. It's a differential equation. And this one's fairly easy to solve, right? So how would we go about solving this differential equation? You can think about it. You can pause the video and solve it on your own. Would be a good practice. But we'll go through it right now. So dq dt, so what I need to do is I need to separate the variables. And once I separate the variables, I can then integrate this and get the answer. Okay. So now I can simplify this expression. dq dt equals negative q plus e times cd over rscd. I can now take this expression and separate the variables, getting dq over negative q plus ecd equals dt over rscd. Now all I need to do is integrate both sides of this expression. And when I do that, I get negative ln of negative q plus ecd, okay, because I've just integrated this 1 over q term with respect to dq, equals t over rscd plus c, which is going to be our constant of integration. Now, we can use our initial conditions to solve for c. So negative ln ecd equals c, right? So because I know at t equals 0, q equals 0. So these are the initial conditions. So if I plug t equals 0 and q equals 0 into this expression, I get this answer for our constant of integration. Now, we can go back and use this expression to get the final answer. So let's make some space here. Okay, so negative ln negative q minus ecd equals t over rscd minus ln ecd. Okay, So this is now my expression relating the potential to the charge. Notice there's no dq dt in here anymore, so this is the solution to the differential equation. And I can rearrange this expression, simplifying it, and you can work out how to do that. It's just a simple algebra and you'll get Q equals ECD 1 minus e to the negative t over RSCD. Okay? And now that we have that expression, that's the charge on the capacitor, Q. So this is charge on the capacitor. ECD, well, that's the, I'm sorry, that would be a large C, ECD. That is the potential step. Potential step is E. The magnitude of the potential step. CD is the capacitance of the double layer, right? And T is time. And RSCD are the same. RS is the resistance of the solution. Right? So what does this look like? Let's think about this. So what happens at time equals 0? So at t equals 0, what happens to this term? Okay. Well, this term goes to e to the 0, right? E to the 0 is what? 1. 1 minus 1 gives you 0. So Q equals 0. Okay, so that's good. So if I plotted Q versus T, right? Q is going to be 0. Now, if I make T very long, okay, what's Q going to go to? Well, if T is infinity, right, e to the negative infinity is going to be 0. So I'll get ECD. ECD. And this, gosh, this is just the definition, right, of capacitance. CD equals Q over E. So if I solve for Q, I get that the Q infinity is just the charge on the capacitor that you get. And the shape of the curve, if you plot this out, looks something like that, okay? And the time it takes to reach that, time it takes to reach sort of close to the maximum charge is the time constant, RSCD. And we call that the RC time constant. And that's really important in electrochemistry. Sorry, here's the plot I've been drawing, showing Q as a function of time, reaching the maximum given by ECD, and this time constant, RC, which is how long to charge capacitor. And you notice as the resistance in the circuit goes up, remember our circuit is a resistor and a capacitor in parallel, or in series, CDL, RS. As either of those increase, either your capacitor needs to take more charge, or your resistor gets larger, it takes longer to charge that system. Now we can take the differential of Q, dQ, dt, right? We take a differential of dQ, dt, and that's going to give us the current that we'll actually measure in our current measuring device. Okay, so if I do that, I take the differential, this first term, right, is going to go away because it has no time dependence in the first term. Take the differential of the second term, to take the differential of the inside function, and multiply it by the overall differential. So I get ECD over RSCD e to the negative t over RSCD. Okay. Of course, those CDs cancel out, right? And you get this final expression. And what does this look like? Well, this part is just an exponential decay, right? And this part has to do with the magnitude of the overall current. So let's plot that. This is going to be the charging current of a capacitor. So if I now plot current versus time, right? Now imagine time is 0, right? What does this term go to at time equals 0? Well, this term goes to the e to the negative 0. E to the negative 0 is 1. So I goes to e over rs. Okay, so this is going to be e over rs. And that makes a lot of sense because initially in this system, remember we have a resistor and a capacitor in series. Initially, the capacitor is uncharged. So the initial current that starts flowing through this system doesn't see any voltage drop across the capacitor. So the current that flows is only going to be dominated by the resistor, and that's just E equals IR. Okay? So the initial current, Ohm's law, right? Initial current is Ohm's law. And then again, if we let this equation go to long times, the current has to go to 0. And it goes there sort of in an exponential decay. And again, right, we can define if this is E over Rs, and this is 1 over E times big E over Rs, so it's decayed by a factor of 1 over E, or by a factor of E. That happens at T equals Rs times CD, or the RC time constant. Okay, so that's again another way to think about that is it's the decay of the current spike that happens when you apply a voltage, right, by closing a switch. So we had this switch here, close this switch from a voltage source while I'm monitoring current. Okay, so that's a simple picture here for an RC potential step experiment with an RC series circuit. Now let's consider what happens when we sweep potential. Okay, this is a little more complicated. We won't go through all the math, but the setup is very similar. E, the potential across this whole device, right? I'm now going to sweep the voltage across the equivalent circuit or across the cell. It's going to be given by, we'll call that V times T. So the potential is going to increase at what's called the sweep rate, which is typically in volts per second or millivolts per second, and this is time in seconds, right? So this is going to give us a linear voltage sweep. And the voltage might be increasing, and then if you're doing something called cyclic voltammetry, right? So you guys may be used to seeing curves that sort of, look like this, right? Or some duck shape that looks like that. I could make it more ideal. Let's make it more ideal. Might look something like this. Okay. That's called a cyclic voltammogram, and then you sweep the voltage back. Okay, so these are very common experiments that you do in electrochemistry, at least in analytical electrochemistry. And so we're going to sweep the voltage in one direction and sweep it back. And we're going to be concerned with the forward sweep here. Now, we can write all this, equations for all this, right? So again, E equals ER plus EC, the voltage across those two things, equals IRS plus Q over CD. And VT equals IRS plus Q over CD. I've just plugged in VT for E, okay? And so we need to do the same sort of thing. We define Q as dQ dt, and then we have to solve this differential equation, right? But now it's a little bit more complicated than before. And what you find, if you do this, is that the current I is equal to the scan rate times CD, double layer capacitance, 1 minus the exponent of negative T over R SCD. Okay, and you can go through the derivation of this in Barton-Faulkner if you'd like. And what you find experimentally is this gives you what's called a charging box. So if you have a electrolyte that you're sweeping the potential of, okay, you have an electrolyte that you're sweeping the potential of, you'll get a response that looks like a box. So why is this? So let's think about what this looks like, right, as I'm sweeping. So imagine I go to relatively long times, right, in my forward sweep. Okay, so imagine I'm starting here. Let's first say time equals 0. So again, time equals 0, that should again give me current equals 0, right? Because time equals 0, this term will go to 1, and 1 minus 1 is 0, okay? And if I go to long times, again, this term's going to go to 0, so I'll get a current that is the sweep rate times CD, okay, at relatively long times. Now remember, I'm on a potential axis here, but I'm sweeping potential with time. So time is increasing as I move from here, the left, to the right. Time is increasing. This is t equals 0, and this is t equals a long time, okay, for this particular experiment where I've reached the steady state current, where this term and this term, the second term has gone to 0 in this expression. And what I'll see experimentally, and you'll be able to measure this, is something that looks like that. Okay. So what's interesting, right, is as we mentioned, the magnitude is the scan rate times CD. That's the magnitude of the height of this line relative to the x-axis. Now, if I switch the potential and scan the other direction, it turns out I'll see the same sort of thing, right? And on the reverse sweep, right, I will see a current that is negative V times CD. So this is an interesting phenomena. You can actually measure this charging box width experimentally, and that tells you the capacitance in your electrochemical cell. It tells you the electrode capacitance, okay? And so often what you'll do is you'll sweep these things back and forth like this, and you'll get experimental data that looks sort of like this. Now, you'll get the closer it is to this, meaning the more ideal your system is, meaning there's no impurities in your system, there's no Faradaic processes happening, there's no other background processes. Often, practically, you'll measure something more like this, where there'll be a little offset, and there'll be a little slope, and at some point it will start to break down, right? And you'll start electrolyzing your electrolyte. But nonetheless, you can still extract from the region sort of where the charging box looks okay and get out a capacitance, okay? Because this distance here is 2 times the capacitance times the scan rate. Now, in experimental systems, you can use this to estimate the electroactive surface area. So capacitance, you can use with some caution, we'll talk about that later, with caution to estimate electroactive area of electrode. For many metal electrodes, CD, we know this from lots of studies, is about 10 to 40 microfarads per centimeter squared. Okay, so if you know that number, if you know the specific capacitance, the areal capacitance, I should say, if you know the capacitance per unit area, and then you measure a capacitance, you can back calculate the area of your electrode, which can be very, very useful. Now, let's take a moment and go back to our simple cell architecture, right? Here, which we drew before. Okay, our simple electrochemical cell. And let's think about RS. So what does this do to? Well, in any electrochemical cell, you have a number of resistances. Call these equivalent resistances. And we'll talk about these resistances. We've already introduced their origin in some of the previous lectures. If you think about a cell, you'll have some resistance, right, due to ohmic natures. For example, the transport of ions and electrons, ohmic resistances. And this is usually what we're talking about when we're talking about RS, especially in this simple cell. In general, though, you might also have resistances associated with kinetics. And you also might have resistances associated with mass transport and other processes. So you can think about an electrochemical cell, an equivalent circuit, that is consisting, in a model sense, of a series of equivalent resistors that describe those processes. And we'll talk more about that. I want to talk a little bit more about the ohmic losses. So if you think about an electrode, think about our working electrode. Okay. So we have our working electrode here, and say I want to plot the electrostatic potential phi here. And this is going to be electrostatic potential. Now, we've been using electrostatic potential a lot, but if you remember, electrostatic potential is sort of the energy it takes to move a charge from infinitely far away from any other charges to the point we're interested in, divided by the charge on that charge. So it's the normalized energy it takes to move a charge to the point we're interested in. And it always depends on what we choose as our reference. Often we choose our reference as something very, very far away, but we can choose our reference for phi, the electrostatic potential, really anywhere. But I won't put any quantitative numbers here. So just think about how phi changes with position through a cell. Okay. So if we have two electrodes, so this is going to be our working electrode. Let's get rid of that. And this is going to be our counter electrode. I have electrolyte in this cell, right? And so if there's no current flowing, we know from Gauss's law that phi in the electrolyte has to be constant. Okay, that's what I'm drawing there. And we know that the working electrode, say we're doing, an oxidation reaction, it's positively charged, the counter electrode gets negatively charged. And we know there's going to be a double layer there, right? At these two different electrodes. And that double layer is going to cause this change in electrostatic potential. So that's actually what I've drawn here now. Let's put some red highlighting there. That's actually electrostatic potential across the cell with no current. Okay, but now let's think about what happens if I do the same experiment and I'm flowing current through this cell. Okay, so if I'm flowing current through this cell, the current will cause, or another way to say that is the cause of the current flow is going to be a gradient in the potential through the cell. So now I know that in my electrolyte, my electrostatic potential actually is going to change because there's current flowing, right? So current is flowing. And so now a portion of the electrostatic potential across these two electrodes is now dropping. We say dropping if it's changing. d phi dx in the electrolyte is not equal to 0, right? Is changing as we move through the cell. Now imagine I come in here with my reference electrode. Right, I put my reference electrode right here. Notice that here there is a delta phi, a change in electrostatic potential between my reference electrode and this position right outside the double layer. Now ideally I'd be able to put my reference electrode right outside the double layer because I'm really interested in electrode processes that are happening here. I'm not really interested in measuring how much voltage is dropped in the electrolyte driving the current. Okay, so this is why we talk about uncompensated series resistance. Uncompensated series resistance is the resistance of the electrolyte in this region, right? Because it's not the whole electrolyte, it's just the part in between the working electrode and the reference electrode. And it can be complicated, right? Because it's a three-dimensional volume that the current's flowing through. So we need to think about that when we think about the resistance of the current flow. It's not a simple one-dimensional model. And there's an excellent paper by Newman excellent chemical engineer, electrochemical engineer. He wrote the textbook, Electrochemical Systems, which is a wonderful reference text on electrochemistry. And he talks about how to calculate these things. Actually, he derived all this stuff in the 50s and 60s for many different systems. And the uncompensated series resistance is associated with this electrolyte volume that's between the reference and the working electrode, and it causes this potential drop. And we call this potential drop equal to IRU. Okay. And then the rest of the potential drop in the electrolyte is IR. We can call it compensated. What's called C, or we can call it solution resistance or ohmic resistance. We can call it a lot of different things. I'm just going to call it. Let's call it I don't know. We'll call it IRC for compensated. And this is, we don't care about this because the reference electrode is not sensing that potential change. I mean, it's changing how much energy we're having to apply between the two reference, between the working and the counter electrode, but we're measuring versus this reference, so we only care about this part. So the name of the game in some parts of electrochemistry, or it's at least important to think about, is minimizing this, right? Because we don't want that to affect our measurement. So we don't want to put our reference electrode really far away. We'd like to put it close to the working electrode to minimize this distance. We'd also like to use very conductive electrolyte. So that's one of the reasons we use 1 molar electrolyte or 0.1 molar electrolyte, is to make sure that this drop here is small. And this can usually be ignored if your current is small. So if you're sort of a milliamp of current in, 1 molar, say, aqueous salt, then this IR drop basically goes to 0 where you can ignore it, okay? But if you're transferring amps of current, amps per current, and you're using 1 molar electrolyte, it becomes hugely important to measure this and correct for it in your data, and we'll go through how to do that. There's other things we can do that, to deal with this uncompensated series resistance. You can actually measure it using either impedance or by looking at the transient response to a potential step, because remember that decay, that resistance is in that decay in the current step, and we can measure that and we can correct for our data. So we can go to our data, we can actually subtract out the component that's due to this loss in the electrolyte. And that's what they talk about series resistance correction, uncompensated series resistance correction in electrochemical data. So you'll see that very often in manuscripts where they say it's E minus IRU. That's saying that they've corrected the data, for example, if that's the x-axis, for the uncompensated series resistance. Okay, so that's it for today, for this lecture. Thank you very much for listening.